After it deals with solutions, this is, we'll call this part 15. It is not found in your textbook, but it is something we need to cover. There are a number of different properties of solutions that we'll talk about in this lecture. The figure you see here has more to do with osmosis, and we'll be getting to that in another section, but also part of this lecture. To begin with, let's remember that solutions have two components. They're composed of a solute, the thing that is dissolved, and the solvent. And specifically for just this lecture, the solvent we'll be discussing is water. The solutes we'll be talking about are solids, and what we refer to as non-volatile solutes. Remember this term volatile. What does volatile mean? Volatile means that it has volatile. It's an L. Volatile means it has a large or appreciable or immeasurable vapor pressure. So I'll just say has a large vapor pressure. We talked about what volatile meant when we were referring to when we first defined boiling point. If you remember, we defined boiling point as a temperature at which the vapor pressure equals atmospheric pressure, and the more volatile a substance is, right, the easier it is to evaporate or to boil, so it has a lower boiling point. So as volatility increases, the boiling point will decrease. It takes less pressure or lower temperature to get it to boil. So when we're talking about these solids here, right, they don't boil at room temperature. You can heat them up, they might melt, but it takes quite a bit to get them to boil, so they're non-volatile. So non-volatile simply means that has a low vapor pressure, and therefore high boiling point. This, of course, would make we'd have to make a bigger deal of this if we were talking about both volatile and non-volatile solutes, but we're only going to be talking about solids. So things like, sodium chloride or sugar or, potassium nitrate, solids at room temperature. All right. So solution is a homogeneous mixture composed of a solute, the thing that's dissolved, we're talking solids, and in this case water, the solvent. Okay. I believe in a previous lecture we also discriminated between other types of mixtures. Solution is one type of mixture. So types of mixtures. We have solutions. We have colloids and suspensions. Okay, so the thing about solutions is the solute, water is a solvent, right? So what differs for all these guys is a solute. The solutes are small particles, ions, or molecules. And molecules can be very large, but we're talking about molecules that are, well, certainly less than 10,000. There's no real defined cutoff, but I'll say less than or equal to, let's say, 5,000 grams per mole. So the molar mass is less than 5,000. You think 5,000 is, wow, that's huge. Well, there are proteins that are 10 or 100 times larger than this, and those would not be actually solutions. Those would be something called a colloid. But other properties of solutions, they are transparent, right? So you can see through them. They do not separate upon standing. So if you just let it sit there on the test tube or in the beaker on your benchtop, it's not going to separate out into the solute and the solvent. Furthermore, they cannot be filtered. The particles, these small particles that are they're so small they'll pass through any filter, and they do not scatter light, something we refer to as the Tyndall effect. So the Tyndall effect is this scattering of light, and solution particles are too small to interact with the light in that way, so they do not scatter the light. All right, so that's some properties of solutions. Colloids, these have medium-sized particles. So we'll say 5,000 grams per mole up to, I don't know, maybe something like 1,000,000, 10 to the 6th grams per mole. All right. Still, these particles are so small they can't be filtered. They can be separated by these things called semi-permeable membranes. We'll talk more about those later. And they do scatter light, so they do exhibit this Tyndall effect. Essentially, the Tyndall effect is if you shine a light through one of these mixtures, one of these colloids, the path of the light is visible. With a solution, you can shine a light through a solution and you will not see the light as it passes through this mixture, but for colloids you can. Alright, so here we've got a mixture, or a solution. Let's say this is sodium chloride, say dissolved in water, so it's aqueous. You should get a laser pointer, shine it through here, and you do not see the path of the light. You might see a little bit of reflection on the glass, but you do not see the path of the light. Now it's going through a colloid. Right, so here's a solution, and here we have the colloid. What exactly is it in this colloid? I don't know. I also don't know why my pen is changing colors like that, but whatever. But you can clearly see the beam as it goes through the light. So an example of a colloid, we'll have other examples later, but milk is a colloid. So clearly this doesn't look like milk, but if you took maybe a few drops of milk and put it in this glass, the proteins and fat that are in the milk would be dispersed and they'd form this kind of cloudy haziness. It could be also proteins. Actually, milk is a mixture of proteins. And anyway, those particles are large enough they'll scatter the light. Another classic example would be dust or smoke or even fog as the light is streaming through the trees, or maybe streaming through your window on a sunny afternoon, and you see the path of the light as it goes through the room, and you see all those dust particles as the light shines on it, and you're thinking to yourself, oh my goodness, I'm breathing in all that stuff. And yeah, you are. When the light isn't as intense, the angle isn't as low, you don't see the path of the light, so you don't see the path of the light, and you don't see all those little dust particles in the air, but they're there. So again, this is dust or smoke. Whoa, what's going on here? Dust or smoke or even fog would exhibit the Tyndall effect. Okay. So all sorts of different types of colloids: fog, clouds, dust, smoke. Shaving cream, here we have a gas dispersed in a liquid. A liquid in liquid, like mayonnaise, butter, and milk. They say liquid, but actually for milk it would also be proteins. So like your blood plasma, the non-cellular part of your blood, has solids. Those solids are proteins dispersed in a liquid, or even cement and pearls, a solid dispersed in a solid. And they have different names. We don't need to focus on the different names for all these types of colloids, but just something to give you an idea of a lot of things that you might have thought were solutions in the past are actually colloids. Why do we call them colloids? Well, because they can be separated by semi-permeable membranes, because they exhibit the Tyndall effect, and what it really boils down to is the fact that these particles are much larger than what you'd find in a solution. And lastly, suspensions. Suspensions have very large particles, so this would be on the order of a cell. When I say cell, I mean like a biological cell. On the order of a cell. They can be so large, in fact, that they can be visible, right? So particles are so large they can be visible. They say visible with the unaided eye, and they will settle out. So in other words, they must be stirred to stay suspended. Okay. Examples include blood, muddy water, calamine lotion. They can be filtered. So the filtering that we've done in the laboratory, those were suspensions. Right? And so they show the suspension particles settling out. Oops. Suspension. The colloid particles, these triangles, and the solution particles stay suspended. I don't want to say they stay in solution, but they say they stay dispersed throughout the mixture. Okay. So the filtered particles here, right? The suspension particles will be retained in the filter. They don't pass through into the filtrate. But colloid and solution particles they are suspended, right? They're not suspended, they are filtered. Colloid and solute particles will pass through. This bag here, they refer to as a semi-permeable membrane. It looks sort of like a balloon. Sometimes referred to as dialysis tubing. We might talk more about this a little bit later. But the semi-permeable membrane allows for, they don't really show it here, but they show the solute particles being able to pass through. The solution and suspension particles can't. Okay. So, summary here. I'm not going to go through all of this, but in terms of the Tyndall effect, or this visibility of the path, solutions do not exhibit the Tyndall effect, but colloids and suspensions do. But if the suspension is concentrated enough, okay, you won't see the Tyndall effect because it's opaque, and in other words, the light doesn't even get through. But if it's dilute enough, yeah, you'll see the suspension particles scatter the light. Here I said colloids, larger molecules up to about 10,000. I said 5,000. I think, I think 10,000 is a bit too high. I think 5,000 would probably be considered a colloid as well, but in any instance, very large. And there's no discrete cutoff as far as the molecular weight between solutions and colloids, or colloids and suspensions for that matter. It's just kind of very qualitative, and we discriminate them in qualitative terms based upon the effect on light or whether they settle or not. Even colloids, particles, they do settle. Right? We talked about dust. Dust is a colloid, solids dispersed in the air, but you have to dust your home. Why is that? Well, because they do settle, but very slowly. Suspension particles celebrate rapidly in a matter of seconds, so you can just sit there and watch the suspension particles come down out of the mixture. But colloids, you could do the same, I suppose, if you really wanted to take the time, but it might take days or weeks for these particles to settle out. Separation, solutions are not separated by filters or semi-permeable membranes. If you wanted to separate, how could you separate solution particles from solvent? We've got a solute, and solvent. How could we separate those? We did it in the lab, but we didn't do it by filtering or use of semi-permeable membranes. Think about it. How do we separate the solute from the solvent? That was by evaporating the solvent. So I just put here evaporation. And remember, I said the solute particles that we're talking about are non-volatile, so we can heat up this solution, drive off the water, and leave the solute particles in the beaker or in the evaporating dish. Colloids, they can be separated by semi-permeable membranes, but not filters. And lastly, suspensions are separated by filtration. Okay, we got a mixture. They don't settle out, and they're too large to pass through a semi-permeable membrane. So that would be a suspension, right? They not separated by a semi-permeable membrane. Oh, and they do not, but they say they do not settle out. I'm sorry, so that would be a colloid, actually, because colloids supposedly don't settle, but they do, but very slowly. All right. Some other properties of solutions. Right? We talked about the tendency to settle, and we talked about the Tyndall effect, how to separate them, and now these colligative properties. There's 4 types of colligative properties we're going to talk about: boiling point, vapor pressure, melting point, and osmotic pressure. Now the term colligative, you can think of colligative. What does colligative mean? Colligative means collective, maybe, right? So these properties, what they depend upon is the total collection of particles in solution. It doesn't matter what kind of particles, it doesn't matter how large they are, whether they're ionic or non-ionic, or what color they are, or any other property like that. What only depends upon is the number of particles in solution. So colligative properties only depend on the number of particles in solution. And I should say, we're talking now about colligative properties. These are properties of solutions. So we're not going to talk about colloids and suspensions with regard to boiling point or vapor pressure or melting point. We're just talking about solutions. And what we'll really do is we'll compare these properties. Of boiling point is certainly a property of a solution. It's also a property of water, right? So what we're talking about here is the effect that a solute has on the boiling point when you dissolve it in water. Okay? So it turns out that the boiling point of a solution is higher than that of the pure solvent. In other words, the boiling point of the solution is higher than that of water. We're talking about water as a solvent here. So the pure solvent we're talking about is water, H2O. So we dissolve something in water, and now all of a sudden the boiling point goes up. Remember, we defined boiling point as the temperature at which the external pressure or the atmospheric pressure equals the vapor pressure. So boiling point is not a constant, but is dependent upon the external pressure. Vapor pressure. Right. Well, vapor pressure, that's the pressure exerted by the vapor when it's in equilibrium with this liquid. So we can draw our little beaker here again. We were talking about this. Right. Here we have water, and there's water molecules that pop off the surface and go into the vapor phase. Right? Now if we were to put a lid on this, we could measure how much pressure these water molecules in the vapor are exerting. And when they're in equilibrium, that is to say, the rate of, so let's go here, water as a liquid goes to water as a gas. When these two rates are equal, right, they're in equilibrium. And what we're looking at is the vapor pressure, of this vapor, right, of this water in the gas phase above its liquid. That's what vapor pressure is. So if we put make a solution, instead of pure water, and we have a solution, the vapor pressure will be lower. Vapor pressure depression. So this goes down, vapor pressure goes down, boiling point goes up, melting point also goes down. Melting point depression or freezing point depression. And then osmotic pressure, we'll have to talk about that separately later. But we've got boiling point vapor pressure and melting point or freezing point depression. This explains how, road salt, why do we use road salt to melt ice? Also explains how antifreeze in your automobile works. All right, so we'll be talking about that in a little bit. Okay. As I mentioned, these colligative properties only depend on how many solutes are in how many solute particles are in solution. It does not depend on the nature of those particles. And what they're showing here in these two pictures here, these two Erlenmeyers, here we have pure water on the left. Pure water. And then on the right we have a solution. So these little red guys are the solute particles. Okay, so we've got some solute particles in here. And if you notice, let's just go ahead and pretend this is a closed system. We'll close that off, put a lid on there. Okay, if you notice, there are more water molecules in the gas phase above the liquid. More H2O in the gas phase. Here we have less water molecules in the gas phase. Why is that? Well, in a solution, let's go back a second, the vapor pressure is lower, right? Why is the vapor pressure lower? Well, there's fewer gas molecules above the liquid in equilibrium to exert that pressure. There's fewer gas molecules, fewer water molecules hitting the sides of the container, hitting the lid, hitting the pressure gauge, or however we're measuring pressure. So if there's fewer water molecules, there is lower pressure. Lower gas pressure. Okay, if you remember, think back to our ideal gas law, PV equals nRT. Pressure equals nRT over V. N is the number of moles, the number of molecules in the gas. As this number increases, pressure increases. All right. Well, if this number decreases, right, we have fewer water molecules, the pressure will decrease. All right. Well, why aren't these guys? Why are there less? Just because we have some of these little red solute particles in here. Okay. Boiling point is defined in terms of vapor pressure. Let me write that down again as well. Boiling point, what is that? This is a temperature at which the vapor pressure equals the external or atmospheric pressure. So when we talked about this at first, right, here's temperature. And this is pressure. and we looked at the vapor pressure of water. As we heated water up, the vapor pressure went up. And remember, we used a chart for that laboratory where we did the collection of gas, collected oxygen gas. And we had to read off from that chart the vapor pressure of water at these various temperatures. And the chart didn't go as high as this, but let's say it went to 100 degrees Celsius. Well, that is the normal boiling point of water. And we'll measure here pressure in torr, or millimeters of mercury. At 100 degrees, this blue line here represents the vapor pressure of water as a function of temperature. At 100 degrees Celsius, the vapor pressure equals 760 torr, which is normal atmospheric pressure. So again, you can think of, I'll put a beaker over here. We've got water molecules above the surface of this liquid. So they're evaporating and they're condensing. Two rates are equal. Maybe steam's coming off. Right? We put a flame under it. Right? Well, when these molecules exert enough pressure to equal the external pressure, we say the liquid boils. So you can think of the external pressure, in other words, the weight of the atmosphere, the atmospheric pressure pushing down on the surface of this liquid, as like a lid pushing down on the surface of this liquid. And when these molecules get enough pressure to push that lid off, we say the liquid boils. All right, so that's boiling point. Solute particles increase the boiling point. They make the boiling point higher. Why is that? Well, because they introduce a new set of reactions, interactions. Instead of just having solvent-solvent interactions, which is what you'd have in pure water, just solvent and solvent. So this is in pure water. All you have is water molecules. So water-water or solvent-solvent interactions, pure water-water interactions. You have now solute-solvent interactions. Okay. Now, if you remember how something dissolves, all right, let's say we've got a salt crystal here, and you've got, right, you've got sodium ions and chloride ions and sodium ions and so forth. And when water interacts with this stuff, right, we get sodium ions in solution and chloride ions in solution, and they're surrounded by water molecules, right? Remember that they're solvated. So the water molecules form these sphere of hydration around these particles. Well, in pure water, all you have is the water-water interaction, what we refer to, if you remember, as hydrogen bonds, right? We have HOH like that. So we have hydrogen bonds between water molecules. So this red dotted line here is the hydrogen bond. And that's what holds liquid water, in the liquid phase. We have to disrupt that interaction to get it to evaporate, to get it to boil. Well, if we dump salt in there, now we have a water solute interaction. And this interaction has got to be stronger. Why has it got to be stronger? Well, it has to be more favorable. If the salt is going to take the place of a water-water interaction, this salt-water interaction has got to be stronger or more favorable. Okay? So now in a solvent, in a solution, we still have the solvent-solvent interactions, the water-water interactions, but we also have this stronger solute-solvent interaction, right? So this interaction here is stronger. That means if we're going to get water to evaporate, we have to disrupt a stronger interaction, which means we have to heat it up higher, which means the boiling point will go up. Okay. Remember playing this game as a kid in the playground? Okay. So here comes big old solute particle. Right? Comes charging across the playground, and here we have 3 little water molecules. This interaction they have here, what do they call that interaction between one water molecule and another water molecule and another water molecule? These are the hydrogen bonds holding these water molecules together. And in order for this guy to dissolve, it has to replace this weaker interaction with a stronger interaction. So we show this big bruiser. I don't know, maybe he's like an 8th grader or someone coming in to beat up his little kindergartners. But the interaction now that this solute particle is going to hold onto those waters a lot tighter. Okay, so we have the solute solvent. This is the solvent. The water is a solvent. Right. This solute solvent interaction is going to be stronger. Okay, solute solute will be weaker. So this is the hydrogen bonds that exist between water molecules is weaker than what you see with the, whoops, water is a solvent. I don't know, let's just say NaCl. Okay, then the sodium chloride, the solute solvent interaction. What does that do? Well, that reduces the vapor pressure, right? Because we have fewer water molecules in the vapor phase, and because boiling point is defined on the basis of vapor pressure, the lower the vapor pressure, the higher the boiling point. So boiling point goes up, vapor pressure goes down, right? They show lower vapor pressure here, fewer molecules in the vapor phase, or in the fewer molecules in the gas phase. And that's because you can think of these solute particles here, these little red pluses, as holding onto the water molecules, keeping them in the liquid phase. Right? If we wanted to boil this, we'd have to heat it up higher to break that stronger interaction, so the boiling point would go up, vapor pressure goes down. Okay, right? So when water boils, the hydrogen bonds have to be broken, and those hydrogen bonds are weaker than what you see in the solute water, solute solvent interaction. Okay, so boiling point goes up, vapor pressure goes down. Right. So you can say here, let's do it this way. Compared to pure water, a solution's boiling point goes up, and the VP, that's vapor pressure, goes down. Great. What about freezing point? Similar kind of thing happens. Two things to keep in mind. We've got the stronger solute solvent interaction, right? Stronger than the water-water interaction. This is wrong. Solute solvent interactions are stronger than the solvent solvent. This should be solvent solvent. Water water. Just say solvent solvent interaction. And the other thing to keep in mind is that when water freezes, it's the pure solvent that freezes. When salt water freezes, the ice that forms on top isn't frozen salt water, it's pure water that's frozen, and it leaves the solute in the solution. The solvent particles are left in the solution. Okay, so because we have to disrupt these stronger solute-solvent interaction. So let's just say here this is solute is, say, sodium chloride. Solvent is water. Because this interaction now is stronger, in order to get it to freeze and get just pure water to separate out, we have to break this stronger interaction, this more favorable interaction, to get pure water to freeze as ice. So we have to get it colder. Okay. So if we think about what's going on here. Okay, here we have water. This is a thermometer, that vertical line, and this is some solution. Okay, the normal boiling point is 100 degrees Celsius, right? Normal freezing point or melting point is 0 degrees Celsius. Okay, so that's for water. For a solution, the boiling point is higher. Right, for reasons we already talked about. So we have boiling point elevation. We also talked about how when we freeze water, it's the pure water that has to separate out, so we have to break the stronger sodium chloride water interaction than just a plain water-water interaction, so we have to get it colder, so the melting point goes lower. Okay. So a couple ways of thinking about this. First off, we remember from this past winter, right? Had a lot of snow and ice. You put salt down onto the sidewalk, and the ice melts. Well, why is that? Well, let's say it's, I don't know, say 20 degrees outside, right? So we're below 20 degrees Fahrenheit. So we're below the melting point of water, which is 32 degrees Fahrenheit or 0 degrees Celsius, right? So we're below the melting point when we're here. We throw ice, or this ice melt, the salt onto the ice, and now in order to get this stuff to freeze, it would have to, say, I don't know, be like 10 degrees. But we're at 20 degrees, so we're above the melting point. So what happens? Well, the ice melts and either runs in the gutter or evaporates off. So by lowering the melting point, we've essentially stretched out the liquid range of water. We've stretched it out on top. We've stretched it out on the bottom. So if you think about it, water is a liquid from 0 to 100, but in a solution, now maybe it's, let's say it's say negative 10 degrees and 100, I don't know, let's say 120 degrees. I'm not sure what it would be in Celsius, but let's just say we've just stretched out the liquid range of water from 0 to 100. Now it goes from negative 10 up to 120. This also explains why we use antifreeze and coolant in our car engines, right? What would happen if on a cold day the liquid in your radiator froze? Well, turns out water expands when it freezes, so it could break the engine. It could, if you've ever had a soda can put in the freezer, say you want to get it cold fast, so you put it in the freezer, and then of course you forget about it. You come back a day later and the thing's exploded, and you got, soda ice chunks all over the place. Well, you don't want that to happen to your engine, so we use this antifreeze. So now instead of water freezing at 0 degrees, it has to get down to like negative 30 degrees. Okay. Similarly, we don't want it to boil. The heat of the engine would cause just plain water to boil. But if we have this coolant in here, now we've increased the boiling point. So instead of boiling at 100 degrees, say it boils at 120. Maybe you've seen cars where the radiator's boiled over and there's big clouds of steam coming out of it and stuff, and you can cook your engine that way. So we've stretched out the liquid range of water by adding this antifreeze coolant stuff. So I just say larger liquid range. Okay. Why is it larger on the top? Well, increase the boiling point because you have to break that stronger solute-solvent interaction to get it to boil. Why is it lower on the bottom? Again, because you have to break the stronger solute-solvent interaction because water freezes as the pure solvent, right? When like sea ice, when the oceans freeze, it's not ocean water that's frozen, it's just plain water, and the dissolved salts and whatnot stay in solution, in the liquid phase. Okay. What does this guy got to do with colligative properties? Picture of Johnny Appleseed. So maybe you know the story of Johnny Appleseed, maybe you don't, but you can click on this hyperlink here and get his story. But basically what he did is he took apple seeds from cider operations. So he wasn't making apples to eat off the tree. He was essentially making apples that would be useful for making hard cider. This was back in colonial periods. And so what they would do is they would take the apples and they'd mush them down, and the sugar from the apples would ferment, and they'd make hard cider. So hard cider was kind of like apple wine. It would be about 12% by volume, 12% alcohol. That's an alcohol by volume. Alcohol. Jeez, I can't spell alcohol. Alcohol. Okay. And that would be fine, you know, you could have apple wine. But then when it gets cold, you know, apples are harvested in the fall, and then when it gets cold in January and February, what you can do is freeze this stuff. Okay, so let's say this is, let's make it easy, 100 milliliters. We freeze it and we get ice on here, and now we've got 80 milliliters of liquid and 20 milliliters of ice. And you could do the math. We remember we had that dilution equation, C1 V1 equals C2 V2. This in fact is not a dilution problem but a concentration problem. Concentration 1 was 12%. It was in a volume of 100 milliliters. Concentration 2, well, let's figure out what concentration 2 is. Volume 2, all that alcohol that was in this 100 milliliters is not in the ice, it's just in the liquid. So now it's 80 milliliters. Okay, and depending upon how cold it gets, remember, as the concentration of the solute here increases, you have to get this colder and colder to freeze. Maybe you've taken I don't know, like vodka is a classic example, and put it in the freezer. It doesn't freeze, it stays as a liquid, right? And that's because of the alcohol that's dissolved. So depending upon how cold it gets, you can get a certain degree of this ice to form, peel off that ice, and now the liquid is going to be more concentrated. I'll let you do the math to figure out what C2 is, but essentially that is how one goes about making Applejack. So Applejack is essentially hard cider that's been concentrated from the normal 10 or 12% to something that's like 20 to 40% alcohol. So Applejack, it's not a children's breakfast cereal, that's Apple Jacks. Applejack is a concentrated version of hard cider. It's like an apple whiskey.